Alrighty then. So now that we've covered some classification metrics, and by the way, I've just put this little paragraph here so you can check it out of when to use different classification metrics, just to kind of break it down in 5 dot points for you. But now we're going to cover some regression model evaluation metrics. And put your hand up if you're ready. I'm holding my hand up too, don't worry. Alright, so let's put in a little heading. 4.2.2. Regression model evaluation metrics. So as always, the documentation is ready to go. So we've got this here. I might put this in here. Another link here. Model evaluation metrics, documentation. Now, I don't want you to be scared like reading the documentation like I was when I first started. If you read this, and there may be a few times where you go through it and you go, wow, you see something like this. You see a bunch of different words here that you don't really understand. You look at a bunch of different examples, you're reading this, and it's like kind of confusing. Don't worry. That's exactly how I started, but after a little bit of practice, after implementing the code like we're about to do, that's why I'm such a big fan of implementing code, I started to understand a little bit more, started to understand about what I needed to use. So, speaking of what we need to use, for regression, we're going to look at 3 different ones. And now these are 3 of the most common, 3 of the most useful. And the first one is R squared, pronounced R squared, or coefficient of determination. Beautiful. And the second one is mean absolute error, which is also known as MAE. And the third one is mean squared error, which is also known as MSE. Wonderful. So now we've got that, let's bring back our regression model. So from Scikit-learn.ensemble, import random forest regressor. Wonderful. We'll set up a random seed so our results are reproducible. Then we'll get our X, which is the feature variables from our Boston data frame. So we want to just drop the target and the axis equals 1. The labels are the target column, or is the target column. Wonderful. And now we'll split our data into train, test, using train test split, passing it X and Y. Wonderful. And then what we're going to do is instantiate our random forest regressor, because we want to build a regression model so we can evaluate it. Wonderful. Model.fit, X train, Y train. Now this is going to give us a warning because we haven't set number of estimators to be in 100. And we're going to run this. Invalid syntax. Classic. From, oh no, import. There we go. Oh, Boston DF is not defined because they've got typos. There we go. See, this is what happens, right? When you're writing code, don't expect to get it right the first time. You're going to get errors. So always remember, if in doubt, run the code and then go back and fix the errors when you need to. Use .score, we've seen this. Y test. Wonderful. And so now R squared can be calculated using, well, actually, where am I getting R squared from? So this is, remember, regression metric number 1. We'll put it here in bold so we know that we're looking at R squared. So that is the default metric here, right? And so the coefficient of determination, R squared of the prediction. Okay, so if we wanted to figure out what exactly R squared was, where can we do that? Maybe we go to Wikipedia. In statistics, the coefficient of determination, denoted R squared or R square, and pronounced R squared, is the proportion of the variance in the dependent variable that is predictable from the independent variables. These are pretty complicated definitions. Well, after doing some research, I created one of my own, right? This is what I'd like you to do, right? If you ever come across something and you see the formal definitions of them, when you look at them from first glance and you're like, this is kind of confusing, is to go in and search and find a way to explain things in your own words. So in my own words, an R squared value compares your model's predictions, here, what R squared does. Compares your model's predictions to the mean of the targets. This is the values of R squared can range from negative infinity, so that's the lowest possible, that's a very poor model, to 1. Now, this is where I love having an example, right? For example, if all your model does is predict the mean of the targets, its R square value would be 0. And if your model perfectly predicts a range of numbers, its R square value would be 1. Whew. If ever you come across something you don't understand, research it, look at different sources, go to Wikipedia up here, read the documentation, right, see an example, but then most importantly, implement it yourself. So I want you not to take my word for it here. For example, if all your model does is predict the mean of the targets, its R squared value would be 0. And if your model perfectly predicts a range of numbers, its R squared value would be 1. So as I said, don't take my word for it, but let's see this in action. So from Scikit-learn, metrics, import, this is another way to calculate R squared, is you could just go R2 score from the Scikit-learn metrics. And then we go here, and we want to fill an array with y-test mean. So the mean values from the y-test data set. So we can do that pretty easily with NumPy. So y-test mean equals np full, so meaning full array of len y-test. So we want it to be the same length of y-test. And then we're going to fill it with y-test.mean. So does that make sense? Beautiful. So if we look at y-test.mean, all this array is an array full of those values. Boom, 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 boom. And so remember what my example said. If all your model does is predict the mean of the targets, its R squared value would be 0. Okay, well, let's test this out, right? Because that's what we do. We're engineers. We test things out. R2 score, y-test. We're going to compare the true labels. All our model did was predict the mean. So very simple model. Oh, it gets an R2 score of 0. Well, okay. And now the second part of that example was, and if your model perfectly predicts a range of numbers, its R squared value would be 1. Okay, so if our model got the exact same predictions as the test values, its R squared value would be 1. So let's see that. We can do this one pretty easily. Y-test. Now, if it got the exact same predictions, if it predicted the y-test labels perfectly, it would end up with a score of 1. So what does this tell us? Well, this gives us a quick indication. This score function, which implements the coefficient of determination, aka the R squared, gives us a quick insight into how closely our model's predictions are to perfect predictions. So, of course, 1.0 is perfect. And so we got 1.0, we saw that here. And if it was predicting nothing but just the mean, it would get 0. And it says here that the value can range from negative infinity. Well, what this means is that if our model predicted completely off the radar, this value can actually go negative. So the mean is actually an okay prediction compared to something that was just predicting all zeros, right? Now that we've seen R squared, it kind of gives us a quick insight into how well our model may be doing, but it doesn't really tell us how far off each prediction is. So to do that, we're going to use mean absolute error. So we'll look at that in the next video.